Thanks, Spencer. Just before I start, I'd just like to acknowledge that some of this is really a summary of some of the work of my current and former, or recently former students. Could I have the next slide, please? As you all know, the late Paleozoic Ice Age is one of the longest Phanerozoic ice houses, and it had a huge impact on Earth's physical, chemical, and biological systems. One important aspect that we're interested in today is the relationship between ice volume and eustatic change. However, getting to that aspect of the LPIA, we must first address some ongoing problems that plague interpretations of this ice age. Next. To better understand glaciation, there are a number of items that still need to be more fully resolved. These questions revolve around identifying depositional facies and environments, as many Gondwana deposits have been misidentified. Items that continue to be poorly resolved include the number of ice sheets that occurred during the Ice Age, identification of individual events in time and space, determining the nature of the transition from icehouse to greenhouse conditions, determining the relationship between ice volume and the distribution of seawater across the world's oceans, determining if bipolar glaciation occurred, which I won't address today, and finally, determining and understanding the significance of local, regional, and global climate drivers. Next. Most studies of Gondwana glaciation use these criteria to identify glacial deposits and hence to determine the glacial record. In many cases, anytime these features are identified, they're interpreted as glacial in origin. Therefore, some researchers plot these sites on a map and then draw circles around these, even if they're single criteria that they're using to define the extent of glaciation. However, the problem with this method is that there are numerous examples that these features are not produced by glacial action, but by other processes. Therefore, we really need to have a multi-proxy approach in looking at glacial deposits to correctly identify whether they were glacial deposits and hence glaciation during the LPIA. Next. Traditional views, which continue to this day, especially shown by this diagram in C by Daniel Starek et al. From this year, hypothesize a single immense ice sheet that was centered over Antarctica that extended outward across much of southern and central Gondwana. Historically, the glaciation was viewed as a single protracted event that stretched from the Visayan to the late Permian. Next. More recently, an emerging view has identified multiple glacial events of 1 to 10 million years in duration that waxed and waned diachronously across the supercontinent, alternating with non-glacial or ice minimal intervals of equal duration. In this view, ice is divided across Gondwana in the form of multiple ice sheets, ice caps, and alpine glaciers. Next. The significance of these two contrasting hypotheses is in understanding the relationship between ice volume and associated eustatic change, as different ice volumes display different sensitivities to climatic fluctuations. The size and number of ice sheets are also important in understanding local versus global driving mechanisms. So in much of this talk, I'm going to attempt to identify whether we had a single or multiple ice sheets. And I'm going to ask sort of a series of questions as we move through the talk. Next. Okay, so the first question is was Antarctica completely covered by a single ice sheet? Because oftentimes, depending on the time frame, especially if we're in the late Pennsylvanian and early Permian, the Gondwana ice sheet is portrayed as a single massive ice sheet centered over southern Victorialand, or SVL in this diagram, and extending outward across Antarctica and across much of southern and central Gondwana. So when we look, go back please, if we look at the basins, and particularly this basin that stretches through the middle in blue, labeled as OR, the Ohio Range, running through to southern Victoria Land, SBL, we can identify basin margins. Basin margins would occur towards the bottom of the diagram and toward the top of the diagram. Toward the bottom is Marie Byrd Land, and if we look at paleo flow indicators from ice in those regions, it suggests that ice entered the basin margins transversely into the depositional basin. In East Antarctica, on the opposite side of the basin, we have the same setting, ice flowing off of the craton and into the depositional basin. Looking at the facies, what we see in these settings, we see basement that is polished and striated, and then it's oftentimes overlain by sheared dimictites. And these suggest then modification and erosion by subglacial processes and deposition in a subglacial setting. Next. When we look at the center of the basin, the situation changes. Subglacial and ice contact deposits are minimal, and what we find are thick shales with loamstones, suggesting ice rafting by icebergs. Sandstones in these deposits are graded beds, suggesting reworking and resedimentation as turbidites, and there's a huge emphasis in terms of folded mudstones and sands that suggests mass transport. And the kinematic indicators for all of those suggest transport down the depositional basin, but with minimal influence of direct ice contact. Next. Some recent work by Libby Ives is consistent with the understanding that I first proposed, that there were ice flowing into the basins from at least 2 ice sheets. And in her diagram shown on the bottom, there is ice coming in from the direction of Marie Byrd Land in the area that she studied. And when you start looking at detrital zircons that David Elliott and others and Zaruli and others have identified, they identify detrital zircons that are coming in out of Marie Byrd Land on that side of the basin where there's flow transversely into the basin, and zircons coming from the East Antarctic Craton entering the basin in the other. So with this, it would suggest that there are at least 2, and if you believe some of the work that Zaruli has had, maybe 4, maybe 5 different ice sheets occurring in Antarctica rather than a single ice sheet. So next slide. Turning our attention to Western Argentina and looking at that area and asking the same question, was Western Argentina covered by ice? We find abundant evidence in uplifts along Western Argentina, late Paleozoic uplifts, lots of ice indicators indicating flow directions by this uplifted area, this hypothetical uplifted area, the Proto-Precordillera. And the facies there, when we look at them, show evidence for subglacial deposition and deformation, as this photo by Ojeda Verde, which is showing a class pavement with a bullet-shaped class that is striated. So lots of evidence in westernmost Argentina. Next. When we move into a little bit farther east and we look at this map in B, a number of researchers have proposed a hypothetical ice sheet that occurred over the Pompeian Arch. And their entire evidence for that is the presence of a Paleovalley system, the Alta Malenzon Paleovalley system, which they suggest was an outlet glacier draining this ice sheet. But when we go in and we look at that particular valley, what we do see is that it does have a characteristic U-shape. However, the U-shape is not cut on basement, it's a modern cut, and it's cut on top of Pennsylvanian and Permian strata. When we look at basement where it's exposed within the valley, as shown in this diagram from Socha and others, what we find is a deeply weathered granite rather than a polished and grooved striated surface for the basement, and it's overlain by this Malanzon formation. Next. Next. Not sure why the slides are wanting to advance, but that's okay. As we look at the Alta as an example, outlet glaciers tend to be uniform in thickness, uniform in width down the length of the valley. And we find it as we come into the modern valley, and which is also being exhumed, the ancient valley being exhumed, we find that the valley narrows, that there are multiple tributary valleys coming in. And in those areas where there are multiple tributaries, the basin, the valley narrows from several kilometers in width down to less than 200 meters in width. And then when we look at the tributary valleys, what we find are boulder supported conglomerates that display downlapping cliniform beds, and those cliniform beds shown in C interfinger with lacustrine rippled sandstone beds, suggesting that these are really alluvial fans or potentially fan deltas prograding out of the basement, out of these tributary paleo valleys. Next. Much of the Alta Paleo Valley consists of thick accumulations of sand. The sands are thin bedded, they're graded, suggesting deposition as originally underflows or turbidites. But most of those sand beds have reworked tops in the form of wave ripples. In a few places, especially where the valley is exceedingly narrow, we do have loam stones, and those loam stones show evidence of having been dropped in, like this 2-meter boulder here that shows ruck structures on both sides of the boulder, suggesting that it did hit and penetrate underlying sediment. But it's being dropped in onto sediment that contains wave ripples. And in this case, the wave ripples are flat-topped ripples, suggesting it's being dropped into exceedingly shallow water. There's also the evidence in C of breccia that is deforming underlying lacustrine sands and suggesting that all of this was rockfall. So our interpretation is that the Alta Paleo Valley was a lake when it was forming or after it formed, that alluvial fans were prograding into the valley, in some cases probably damming the valley, forming the lakes, and that there was abundance of rockfall in certain places within the valley. But we find no evidence whatsoever of a glacial signature within any of the deposits. Next slide, please. When we move farther to the east, glaciation continues long after it disappears in western Argentina. And when we look at the Paraná Basin, there are two hypotheses for glaciation of the basin. In B, we're seeing the Paraná Basin and the hypothesis by Michelle Holtz and others that glaciers coming out of Africa extended across the entire basin to its western margin in Bolivia, Paraguay, and western Brazil. The other hypothesis is that shown here by Rocha Campos and others that suggests that there were glaciers sitting on basin margins that extended short distances into the basin, and that glaciers occurred on both eastern and western margins of the basin. Next. When we look at the eastern margin of the basin, it's known as the Itararé group, and it's shown in this map as the red strata. There's abundance of ice flow indicators. All of those ice flow indicators in eastern Brazil, eastern Paraná Basin, suggest flow coming out of Africa and across basin margins into the Paraná. That's also true if you look at the southern margin. There's indicators suggesting ice flow northward out of Uruguay and into the Paraná Basin. The facies there show when we have surfaces that are exposed, they are grooved and plowed, and they suggest subglacial deposition and deformation, an abundance of dimictites that are interpreted as subglacial in origin, and then some of the work here by Nick Fedorchik showing glacial tectonic structures, so subglacial deposits and ice contact deposits. Next slide. In Uruguay and in the southern portion of the basin, we find evidence that the basement is sculpted into streamlined pictures by this work by Nick as well as Mario Assini. And from this work and from the work in the ice flow indicators, it appears that at least two lobes, possibly maybe two different ice sheets, extended ice into the Paraná Basin. Next. When we move out into the depositional basin, short distances, what we see are we start losing the signature of glacial contact and subglacial deposits, and we start seeing mass transport deposits and resedimentation of material from the basin margins. There are shales with drop stones, and when we do see modified surfaces, what we end up seeing are grooved surfaces, but when you go perpendicular to the grooves, those grooves pass out into unmodified surfaces, suggesting that these are not subglacial, but these are the result of iceberg keel marks. Next. Jumping to the opposite side of the basin, looking at the Aquidauana Formation along the western margin of the basin, many of the ice flow indicators are really giving trends rather than true directions. And so it's difficult to identify where glaciers moving in or out of the basin. But when we start looking at other deposits, when we start looking at graded sandstone beds and mass transport deposits, the flow directions and the kinematic indicators suggest flow or slopes from the western margin into the depositional basin. So this suggests that there were at least two, possibly three ice centers feeding ice to the Paraná Basin during the late Paleozoic and near the end of the Pennsylvania. Next. So if we look at numerous basins around Gondwana, we find similar scenarios, similar situations. And what we would suggest is that Gondwana was not covered by a single ice sheet, but it was dominated by multiple ice sheets, ice caps, and in some cases, alpine glaciers. We would identify that glaciation occurs on the order of 1 to 10 million years, and that it's separated by non-glacial events of equal duration. Glaciation started in northern Africa and northern Brazil in the Devonian, and then extended across Gondwana throughout the late Mississippian into the Pennsylvanian, and then extensive ice in the late Pennsylvanian moving into the early Permian, and then ice disappeared across much of Gondwana and continued into the late Permian only in eastern Australia. Next. So let's take a look at the transition. The transition, this slide. The transition begins in western Argentina. The dating of that event is by Eric Wilbronson. And what we see there is that ice disappears near the Bascurian, the Mississippian Pennsylvanian boundary. We move eastward to the Paraná Basin. Work by Neil Griffiths in the southern Paraná Basin suggests ice disappeared there near the Pennsylvanian Permian boundary. And then additional work by Neil in South Africa indicates that it continued, glaciation continued into the Artinskian and ended near the Artinskian Congurian boundary. So there's a stepwise deglaciation going on. And why ice disappeared in western Argentina first may be in part because we had a developing orogenic belt, uplift and collapse of mountain belts, and accretion along western Gondwana and development of multiple arcs that were accreted to the continent. creating both orographic effects as well as rain shadows, limiting potentially glaciation farther to the east in Argentina because of this precipitation shadows. Next. The transition, go back one please. The transition in Western Argentina occurs in the mid-latitudes. Polar Gondwana was not glaciated at that time, and glaciation, the maximum glaciation in Eastern Australia is in the early Permian with large ice sheets in what was Fielding and Frank's P2, P1 and P2, and then during P3 and P4, when glaciation disappears elsewhere in Gondwana, they had small ice caps. But again, noting that glaciation was not occurring in Western Argentina, suggesting that drivers may not entirely be global, that local drivers may also be important. Next. Okay, what's the relationship between ice volume and use to sea? Ice is a Bingham plastic. As ice is deposited and starts building upward, it will have a yield strength that the basal ice will exceed as the ice thickness is greater than 40 meters. And at that point, ice begins to flow. So if you want a big pile of ice, you have to have a increasing size of a ice sheet footprint. And so you can look at a footprint and that will give you a particular volume for ice. So if we convert different ice areas and hence volume into sea level equivalents, this diagram in B shows different sea level changes that can be expected with either complete growth or complete destruction of ice of 10 meters, 30 meters, 50 meters, 100 meters, or 200 meters. And what you start seeing is once you exceed 50 meters, you start needing tremendous amounts of land area covered by ice to have those sea level equivalents produced. And you have to have complete growth and complete destruction of that ice sheet. Next. Okay, that's if it's a single ice sheet, but the evidence suggests that it's really multiple ice sheets and maybe up to 25 or more different ice sheets depending on the time frame. And as you divide ice up that has this particular footprint into multiple ice sheets, you start losing ice volume. So in B here, if we want to produce a 100-meter change in eustatic sea level, a single ice needs a footprint area of 20.3 times 10 to the 6 kilometers squared. 10 ice sheets, 31.1. 25 ice sheets, and we're almost double the land area covered in 37.1 times 10 to the 6 kilometers squared. So having ice to produce a 100-meter change in sea level, if we've got multiple ice sheets, we need a huge area of Gondwana to be covered. Next. Okay, so what's the response of sea level? And typically, I've always thought of it as this equal layer of water distributed around the entire globe. But if we're looking at the Pleistocene and the Holocene, and we're trying to get at sea level change, it's really something that's called glacial isostatic adjustment if we want to understand what sea level is doing in any one place. And it's really quite a complex interaction between the ocean and ice sheets and loading and the asthenosphere. So in general, with loading by ice and or ocean water, we have a isostatic response to loading by the ice sheet. We have redistribution of the asthenosphere. If we have loading and unloading by water in the oceans, we have a similar reaction. And for the ice sheets and the mass of the ice sheet will attract the water, and it will create a sea level high within several thousand kilometers of that large ice sheet. As the ice sheet starts to dissipate, that bulge of water will return to the world ocean and sea level will go down close to the ice sheet. And as it's redistributed across the entire globe, it's not necessarily an even layer of water across all of the globe. And really, we have to think of it as being redistributed based on the geoid. And the geoid then is the shape that the ocean surface would take under the influence of gravity and the rotation of the Earth. And if we look at the modern geoid, we find that there are areas where there are depressed ocean surfaces in terms of elevation. The northern Indian Ocean, it's almost 100 meters lower than average. The northern Atlantic, it's almost 100 meters higher than average. Next. And if we start thinking, next please. If we start thinking of the GIA response, it has to be thought of as what's happening in the fingerprint from individual ice sheets. And so if the Greenland ice sheet is melting, and we start looking at the ratio of relative sea level change to global mean sea level change today, we find that there is a drop in sea level several thousand kilometers away from the Greenland ice sheet. There then is a progressive change into the southern hemisphere, and then ultimately we start seeing that there are highs in the southern hemisphere. The West Antarctic ice sheet has the opposite effect. As it begins to melt and that bulge of seawater goes down, sea level drops close to the ice sheet, and then sea level highs in the opposite hemisphere in the northern hemisphere. So there's not this equal distribution of water in the world's ocean. The late Paleozoic hasn't been modeled as of yet, but there has been some modeling in the Ordovician by Pohl and others, and Kasimovian and a few others, and their work suggests lows in the southern hemisphere for the Hernanchian glaciation and unequal distribution of water in various highs across the geoid at that time. If we think of the late Paleozoic and that it's multiple ice sheets, we really start running into problems because each ice sheet has its own signature, and each would then have its own glacial isostatic response. So I think that's kind of exciting because it really tells me that the late Paleozoic is even more dynamic than I ever imagined. Next. Okay, just briefly talking about global drivers, and I'll try to keep this short because I really haven't gone into detail to explain anything. When we start thinking of first order drivers and we start looking at the distribution of glaciation and when glaciation occurred in Gondwana, we can first think of the positioning of the continents as a first order control, and we can think of the CO2 and insulation and greenhouse insulation across the Earth for driving glaciation, and these 1 to 10 million year long glacial events. Fluctuations within those are most likely the result of orbital parameters. Next. The equilibrium line elevation is also a regional control, or excuse me, a global control, and it's really telling us what the insulation is for any particular point on the surface of the Earth, going from the North Pole across the equator to the South Pole. And in B, it shows how the equilibrium line elevation rises and falls with latitude. And that then represents how much insulation is coming into the system at that point, and will it allow an ice sheet to grow. Those drivers, though, also require that we have a moisture source. If we don't have a moisture source, we can't grow an ice sheet. And in part, the orographic effect may help deliver ice sheets and help, deliver precipitation and allow for the growth of ice sheets in certain areas. And it may inhibit the growth of ice sheets, such as in the Pompeian Arch in Western Argentina, because of a precipitation shadow. Next. Okay, so what was the late Paleozoic ice age like? Numerous ice sheets scattered across Gondwana, multiple short glacial and interglacial events of equal duration. Glaciation started in northern Africa and northern South America. It was stepwise in terms of deglaciation, and it finally ended in eastern Australia in the late Permian. During glaciation in the late part, the middle and late Permian, polar Gondwana was not glaciated, suggesting that perhaps regional drivers are just as important in some region as global drivers. And then this whole concept of GIA, which hasn't really been extended to the late Paleozoic, suggesting that there is not an equal distribution, an equal layer of meltwater that is distributed across the world's ocean, but it's driven by gravity as well as the rotational effect. So let me end there. Thank you.
All right, thank you, John. Questions? Okay, Bill DeMichael has a question.
Bill always has a question.
I'm playing the role of Spencer yesterday. I always have a question. Some years ago, John, you published a paper suggesting, and you sort of alluded to this with your ice volume and sea level, that there might not have been enough ice to drive cyclothem changes, particularly during the early part of the late Pennsylvanian. Have you changed your mind on that, or do you have any further insights on that?
Yeah, back in the early 2000s, the dating of the late Paleozoic Ice Age was really poor. It was based primarily on pollenology, and then it was a overlying deposits in most cases. I think because of the work of people like Eric Bronson, Neil Griffiths, Joe Martin, Metcalf in Australia, and a number of Brazilians as well, that we have a better understanding of some of the timing of glaciation. And so I don't think we have these really long intervals that I initially identified as glacial 1, 2, and 3. I think glaciation is more complex, more continuous than that. There are what appears to be glacial and non-glacial intervals that you can correlate over long distances. And I think Neil Griffiths will probably talk somewhat about that on the last day with looking at the Paraná Basin and the Karoo Basin. Was the late Paleozoic glaciated? I think there was glacial evidence for that, especially in a basin like the Paraná. Glaciation ends in the southern part of the Paraná Basin by the Pennsylvanian Permian boundary. That means everything is done in the southern part of the basin by then. So the glacials have to be late Pennsylvanian in age. The evidence in southern Africa, there are glaciations going on. There are interglacials or non-glacial events, but they're not these 20 million years intervals in between. So I think glaciation was more continuous than I originally thought based on the data at the time. And I think it's an idea that will continue to evolve as we get better and better dates.
Great, thanks, John.
Well, let me ask, maybe I didn't quite understand. It strikes me you have this cyclothemic sequence in the mid-continent. And in my simple-minded view of it, it looks like glacial, interglacial, glacial, interglacial, with a very regular rhythm to it. What do you think is going on there?
I do think that glaciation is probably driving most of that. How much in terms of sea level change? How much was sea level changing worldwide during the late Paleozoic? And I mean, if we're looking at modern, and the Greenland and Antarctic ice sheet have relative sea level changes locally that are 1.4 times the average amount of change in sea level. That means you could have huge changes depending on where you are and where ice sheets are waxing and waning. I don't think there's much evidence for glaciation in Siberia. I don't see that. I think most of the glaciation is occurring in Gondwana. There were probably uplifts. Lynn might argue that there were uplifts that were causing glaciation in the ancestral Rocky Mountains. Ron, in our discussion with him earlier, the Appalachians had to have glaciation. Those glaciations, though, that's really small volumes of ice, and you and I couldn't go out to the ocean and measure the fluctuations of an alpine glacier waxing and waning. It has to be ice sheets. And the only place that we can really put ice sheets is Gondwana. So I think Gondwana glaciation is driving it, but we don't really take into account aquifer used to see, which also occurs on a similar time scale. But I think that concept is still in its infancy, and I just don't understand that much. I think it has to be glacial eustatics or glacial isostatic adjustment that's being driven by Gondwana glaciation.
And then, correct me if I'm wrong, it's in the Sakmarian that you lose enough ice after the Sakmarian. You don't think there's enough ice to drive global eustasy. Am I right or wrong?
There's less ice after, well, you have it continuing in the Karoo Basin. Neil Griffiths has identified glaciation now and the timing until the almost into the Kungurian. So at least in there, you've probably got some ice sheets that are still around. But once you get into the Kungurian and middle and late Paleozoic, there's just no evidence for any ice anywhere except Eastern Australia. And the evidence for ice in Eastern Australia during Australian P3 and P4, the evidence is glendonites and ice rafted material. Ice rafted material, we underestimate how much material sea ice transports. Alan Archer, if you've ever listened to him, will show you pictures of boulders on tidal flats that are 9 meters in diameter transported by sea ice. And so just because you have ice rafted material doesn't mean icebergs. And glendonites we tend to think of as cold climate indicators, but there's some recent papers that suggest that they can occur at 20 degrees C. They're currently forming off the coast of Brazil and Nigeria. They form in cold water seeps in California. So I think it was cold. I think the only place that we could possibly have evidence was Eastern Australia, but polar Gondwana, there's an abundance of plants. There's no evidence for ice damage in any of those plants when you're looking at the mid and late Permian. There's just no evidence for glaciation at that time in polar Gondwana.